All right, so if you know anything about the orbital geometry, if you know anything about the atomic geometry, and electron domain geometry, that can give you a little bit of an insight into the different hybridization. So electron pair geometry, I want you to be able to connect your electron pair geometry to the hybridization. So the common electron pair geometry that we talked about a linear molecule, a trigonal planar, a tetrahedral, trigonal bipyramidal, and octahedral. Now, the hybridization of all these different things. Well, a linear molecule is going to have sp hybridization. Trigonal planar is sp2. Tetrahedral is sp3. Now keep in mind what this is. This is s orbital plus a p. This is s orbital plus a p plus a p. S plus a p plus a p plus a p. Okay, so when we get into these higher order things, think about what those looked like. When you talked about a tetrahedral molecule, you talked about something like CH4. Okay, so there was 1, 2, 3, 4 hydrogens surrounding a central carbon. When you talked about trigonal bipyramidal, well, that was something that had something like PCl5. That has 5 different things around it. Compare that to CH4. CH4 only has 4 things around that central atom. Okay, so you're kind of building on different things here. So sp3 hybridized is your tetrahedral molecule. A trigonal bipyramidal is going to be one that's sp3, but then it's something else. It's going to include another orbital. And when it comes to that next level orbital, it's going to be a d orbital. So you've got sp3d hybridization. So what that means is that this orbital is s plus p plus all 3 of your p orbitals, plus the next is your d orbital. Octahedral, you've got 6 things surrounding your central atom. So you've got an s orbital, 3 p orbitals, 2 d orbitals. sp3d2 hybridization. So some examples for each of the following compounds indicate the hybridization of on the central atom. We were talking about the central atom, so you need to be able to identify that when you put together Lewis structures. So we've got H2O, CO2, CH4, SO3. Okay, now when we look at these individual molecules, what I want you to be able to do is basically be able to draw that molecule. So draw the Lewis structure of that molecule, then take it the next step and make sure that you know where any lone pairs of electrons are. Now H2O, that's an sp3 hybridized molecule. Why is it sp3 hybridized? Well, what are the number of things surrounding that central atom? Well, what is our central atom? That's an oxygen. We've got 2 hydrogens. And then we've got 2 lone pairs of electrons. So you could look at this as an oxygen is a thing, another oxygen, or I'm sorry, a hydrogen is the thing, another hydrogen is a thing. A lone pair of electrons is an electron domain, so a third thing, and then finally a fourth thing, another lone pair of electrons. So that is sp3 hybridized. You've got an s orbital, a p, a p, a p. So you have 3 p orbitals and 1 s orbital, hence it is sp3 hybridized. Okay, now carbon dioxide. Let's see what that looks like. Again, we're talking about this about the central atom. So carbon dioxide. You have 2 things surrounding it. So that's an s orbital and a p orbital. So that is sp hybridized. CH4. Well, this is one that we've actually already kind of talked about. There are 4 hydrogens surrounding our central carbon. So that is an sp3 hybridized molecule. Lo and behold, I am correct again. Now, finally, SO3. So when you draw that molecule, ultimately, you're going to come up with something that looks a little bit like this. You might look at that and say, oh, well, it's got 3 things around it. Surely it's got to have a lone pair of electrons around that central atom, but it does not. You've got 3 double bonded oxygens. When you have those 3 double bonded oxygens, how many things do you have surrounding that central sulfur atom? SPP. You have 3 things surrounding it. So SPP. So there are 2 p orbitals, 1 s orbital. You're combining those to make an sp2 hybridized molecule. All right. Next up is, oh yeah, you can use the shape of the molecule or the shortcut. It's important that you be able to draw that Lewis structure in order to get anywhere with these problems. Next up is a little bit of a complicated idea, and this is the sigma bonds. So a sigma bond, the electron density is around an internuclear axis. And what we've got here is two examples of nuclei. So we've got a hydrogen and a hydrogen. The electrons are shared between these two nuclei. Okay, so what we've got is, or our highest electron density is between those two nuclei. And if we take H2 as an example, where are those electrons? The valence electrons, the only electrons that hydrogen have here, are in those overlapping s orbitals. Okay, now if we look at something like this, this is the overlap of an s and a p orbital. If we look at something like this, this is the overlapping of p orbitals. Okay, so that's two overlapping p orbitals. Now, what gets fairly complicated is whenever we are looking at the sigma bonds and trying to define what those electrons are. The way that the kind of shortcut for sigma bonds is to define a sigma bond as the first bond. So the first bond between nuclei. So if you talk about, well, actually I'll get to that in a little bit, but it's the first bond between two nuclei. The pi bond, in a pi bond, the electron density is above and below the internuclear axis. Okay, so now we look at this. We've got our internuclear axis where we have a pi bond. We have sharing of electron density above here and below an internuclear axis. I'm going to go ahead and draw a little X here. That's our internuclear axis. This is a nuclei, this is another nuclei, and we've got electrons being shared between those two. Now, another way that you can look at a pi bond or understand a pi bond is to think about it as a pi bond is the second and third bond between individual nuclei. Okay, so a pi bond between, what we have here is a pi bond between two p orbitals. Okay, so as we go on from there, when you talk about sigma and pi bonds or sigma and pi orbitals, well, a single bond is composed of one sigma bond, hence why I described it as the first bond. A double bond is composed of one sigma bond, your first bond, and one pi bond. Now, like I said previously, a pi bond is considered your second and your third bond. So what you could say is a triple bond is composed of one sigma bond and two pi bonds. So as an example, if we look at something like this, count the number of, say, sigma bonds and count the number of pi bonds. So this is a molecule known as ethylene. Well, ethylene, from an electron density standpoint, looks like this down here. Now, if you're asking yourself, well, how many sigma bonds and how many pi bonds are there? Well, sigma bonds, which I'm going to draw my sigma symbol, I'm going to use red to highlight those sigma bonds. There's 1, 2, 3, 4, 5. So there are bonds between the internuclear axis of carbon and hydrogen. There are a total of 5 sigma bonds. How many pi bonds? Well, are there any pi bonds between carbon and hydrogen? No, there are not. There is one between carbon and carbon. So sigma and pi bonds are something that you'll really use a lot when you go on to organic chemistry. And it all has to do with those overlapping orbitals. So an s orbital and a p orbital, or sp orbital, or an sp2 orbital. All of this is kind of a compounding information that builds upon itself. But being able to identify the sigma bonds and the pi bonds, that's maybe one of the more important parts about General Chemistry 1 and looking at a molecule. Let me go ahead and draw that write that last thing out there. But other than that, that I believe is almost that is the end of chapter number 9. So understand the fundamentals of this, and I think you'll be in great shape. All right, well, have a great afternoon.